Now let's talk about the goodness of fit test. Remember I said that there are two different types of chi-square tests. You did both of them in the lab, and we'll start with the goodness of fit because that's the first one that you did in the lab. And so if we look at the checklist, number one, you have one variable with two or more discrete, that is, non-overlapping categories. So what you really have to take away from this first criteria is that you're only looking at one variable. That variable has categories, and the categories don't overlap. So if we were to take a variable like age, right? Normally, we don't think of age as being categorical, right? Because we think of age as being continuous. If I ask you how old you are, you'd probably give me a number, like I'm 18, I'm 21, I'm 19, etc. You probably wouldn't say I'm young, all right? Well, maybe when you get to be my age, you might say something like that. But most of the time, when we think of age, we think of a number. And that's true. Age is a continuous variable. But of course, we can take a variable that's continuous and group people into categories. So we could group people into young, middle, and experienced, right? So young we might define as under 18, under 18. And the reason why I'm stressing that is because the next category could be 18 to 59, right? So notice that under 18 means 17.9999999. 18 to 49 would be a non-overlapping category. If you're 18, you're in that second category. Anything less than 18, you're in the first category. So our third category, let's see, did I say the second category is to 49? Let's just expand that and say the second category ends at 49.9999999. All right, that means the next category would start at 50. Okay, so you see how it's not overlapping? So no matter what age you are, you can only be in one category. All right, now from your sample, because you're collecting data, right? That's why we use statistical tests. It's because we have data that we want to analyze. So from your sample, you are observing, that means you're just counting the number of cases that fall within each category. So the frequency of each category. So if you go around campus and let's say you just want to tabulate the number of different majors on campus, well, you have a list of the different majors, and what you're doing is you're counting the number of people that you come across as belonging to each major. Does that make sense? So let's ignore the people who are double majoring, and I don't know if there's anybody crazy enough to triple major, but we'll exclude them too. So you have a list of, let's say, 26 different majors. So you're just going around campus and you're counting how many people are in this major, how many people are in this other major, etc., etc. So in the end, you end up with a case count, a frequency for each major. Now I got to point out that even though that's one variable, right, number of people in each major, you really would not want to do a chi-square goodness of fit if your variable had 26 different categories. The reason for that is that, one, it would be really, really hard to interpret to see what's going on with 26 different categories. But the second reason is you would likely come across a problem. One of the assumptions, which we'll get to in a minute, but one of the assumptions of the chi-square test is that you don't have an expected frequency less than 5. And expected frequencies are different from observed frequencies. We'll talk about that difference in a minute. But just note that the more categories you have, the more likely you're going to find an expected frequency less than 5. And that means you now have a violation. All right? All right, so we would keep the number of categories probably to anything between 2 and maybe 6 categories, typically. The point with this second checklist bullet point here is that you are simply counting the number of people in each category. Doesn't have to be people, could be dogs, cats, whatever, but you're counting the number of times each category occurs, the number of people in each category, or whatever, a case count, okay? Those are called your observed categories because you are observing with your own eyes how many people are in each category. Now what you want to do is you want to answer the question of whether the observed frequencies, those that you counted, are statistically the same for each of your different categories. All right. So again, you're looking at your observed category, your observed frequencies within each category. All right. So let's just say we have A, B, C, D. Those are our 4 categories. And let's say we have 10 people in the first category, followed by 12, followed by 8, followed by 6. These are your different frequencies, right? The number of people in each category. Are those actually statistically equal to one another? Right? That's what we want to know. Now, notice the question is not about the means. These are questions about frequencies. You have to know the difference between a frequency and a mean, or between a frequency and a score, right? Frequencies are just counts, 1, 2, 3, 4, 5, okay? Not scores on a test. Now, the second use of this goodness of fit test is to see whether or not the frequencies that you got for each of your categories is the same as the frequencies for some other distribution. And that other distribution can be a real distribution, or it can be something hypothetical. Like you might get, frequencies for different, scores on a test, like A, B, C, D, right? Number of people get A, number of people get B, etc. And you might want to know, okay, that's the distribution for our class. What about for this other section of statistics? What is their distribution like? Is our distribution of class grades different from theirs? So that would be comparing it to a real existing distribution. But there could be situations where you want to compare it to a hypothetical distribution. And that distribution might be, for example, if we had, let's say, age where it's ordinal. So we have young, middle, and old. And we want to know if that distribution is basically normally distributed. Now, normally when we talk about a normal distribution, we talk about it being interval or ratio. And I said, well, if we group people into age, young, middle, old, now that's ordinal. But because it's ordered, we can just look at the basic shape and say, well, if it's normally distributed, we should have the most people in the middle category, right? And fewer people in the young and older categories. And so we could still look at that basic shape and compare it to what we should see if, in fact, it were normally distributed, all right? Even though age, as we've defined it, is an ordinal variable. Okay, so these are the 2 uses of the goodness of fit test. Either you want to test the hypotheses that regardless of how many different categories you're looking at, those categories have equal frequencies statistically, or you have a variable with certain frequencies of the different categories, and you want to know if your frequencies for the different categories are the same as some other distribution. All right? Don't forget, though, in both cases, when we look at your variable, we're only looking at one variable. Okay? Your variable, the one that you looked at the observed frequencies for, there's only one of them. Okay?